Okay. All right. Welcome back, everyone. So we have the second lecture by Professor Sriram Ramaswamy, who is going to talk about apolar order parameter. And Sriram, take over.
I'm going to, basically I'm going to go over to, remember last time I really described a framework, and this time I'm going to apply it to two problems. One is flocking in fluid. Basically, if you remember, what I said was that, you can build either a particle-based or a continuum theory of how things order and start moving collectively. And I wrote down these somewhat complicated equations. I'll go back a little bit and start from, what I told you was that, if you have a little vector field P that's describing how something is pointing, then on general grounds, you can write down a theory for how it will order if it is just governed by some free energy functional F. And then I said, if it is active, then this kind of term is permitted, and this term makes the order carry itself in certain directions. This coefficient being proportional to that mysterious quantity delta mu, which I said is the driving force for the energy conversion process or chemical reaction, or whatever it is in the system. And I said that you can also derive those kinds of equations as the continuum theory of a set of rules where you have little arrows that are trying to line up with each other. So each arrow tries to line up with its neighbors like this, and then it moves in the direction in which it's pointing. And the claim is, I won't go over this, but the claim is this kind of a agent-based model gives you this kind of a field theory. Okay, with the kind of free energy functional that I told you earlier that favors the formation of order locally, the coherence of that order from one point to another in space, and a coupling between that order and concentration gradients. And so what happens is, because it's active, if you include the concentration or number density field of the particles and their orientation, two kinds of those new terms or active terms that I told you about are permitted. One which says the order can carry itself, the other that the order can carry particles. V0 and V1 at this level of analysis are purely phenomenological parameters, both proportional to how strongly the internal energy conversion process, the chemistry, the force on that chemical variable, they're both proportional to that. They're both so-called active terms. And then I said, this is all very well, but the point is, this is assuming that these interactions and alignment and movement are taking place kind of in a blank medium. It's like the particles are on some dry terrain and trying to move. Very often, collections of organisms interact and start moving in the same direction in a fluid medium. Okay? So the point is, if you have a fluid medium, I already told you there's a bunch of other dynamical slow variables, namely the densities of conservation laws of energy, momentum, mass and momentum. And the question, therefore, is, if you couple this kind of physics to a fluid, what happens? Right? And this is very old work, but it sets the basis for the more new things I'm going to tell you about. So then I started telling you that an object exerting self-propulsion and moving through a fluid looks either like this guy. You can see my cursor, right? So it looks either like this guy or like this guy. Generically, the simplest orientable object that swims through a fluid either pushes fluid backward and moves forward, or pulls fluid towards itself and moves forward. And both of these, if you look at it from the point of view of writing down an equation for the combined forces on the particles and the fluid, because it's only that momentum that's conserved, the total momentum of particles plus fluid, in the equations for that momentum density, this kind of structure will be a dipolar force density, because you've got a swimmer and you've got the fluid, and the total force is zero. So the force density will be distributed. This bit will be a force that pushes forward. This bit will be a force that pushes backward. The total force is zero. the force density won't have a monopole moment, it will have a dipole moment. So we'll write down equations of motion for the orientation. We're going to imagine a collection of these particles. And we'll write down equations of motion for their collective orientation. So we'll take a coarse-grained picture. We won't look at each individual particle. We'll write down equations for an orientation field, a hydrodynamic velocity field of both the particles and the fluid. And these are the two important bits. And in principle, the number, density, or concentration of the particles. Okay.
Sriram?
Yeah.
Yeah. So when you have a system like this, for both pushers and pullers, you are going to get a force dipole, right? From the figure that I see here. So is there any difference in the force dipole itself, or is it something that reflects the fact that they are pushers versus pullers?
So, I mean, the magnitude will depend, the magnitude is a property of the swimmers, right? There'll be some strength of the force dipole. And that, I don't know if Prerna has given a talk. Did Prerna talk in this school?
Yeah.
So Prerna talked about particles like this one, pullers. Other people might work on bacteria which look like this. So there are the individual force dipoles are characterized by an axis and a strength, right? And that strength has both. So that strength is how strongly it's pushing or pulling along its axis. And so there's a magnitude, a sign, and an axis. All of those are there. But at the level of collective modeling, that will be subsumed in one coefficient, which relates the orientation to the stress.
Got it.
Ways that you can describe order, you can think of two ways of describing order. If you've got a bunch of arrows like this, then if you take some local region, and let's say each individual object has a unit vector n alpha, if you take some little coarse graining region here and average all the n alphas in there, that will be some vector, right? Because you're adding a bunch of unit vectors that are not pointing parallel to each other and then dividing by their number. That object isn't any longer a unit vector because the sum of possibly not perfectly parallel unit vectors. And you add those unit vectors and divide by their number, the number of them, and that will give you some field P of R, whose magnitude will be the strength of local order and whose direction will be something we'll call the director. Sorry, it will be, so I didn't have a slide here, a line here mentioning that. There'll be a magnitude and a direction, okay? You can also have a more complicated descriptor of the order, which I will talk about later in today's talk. Supposing you have a bunch of things whose axes are locally aligned, but whose head and tail aren't necessarily all aligned the same way. Like, look at these guys. There are a bunch of arrows. The axes are aligned, but some of them have head that way, some of them have head this way. Then clearly, this average will be zero if they're perfectly cancelling. But if you take NN, so if you take a tensor whose components are the individual N, I, and J, that average won't be the same as delta, 1/3 delta Ij. Right? If you, I don't know if I can, just look at this expression. N alpha is a tensor whose components, ijth component is the ijth is n alpha I into n alpha j. N alpha is the unit vector associated with particle number alpha. N alpha times n alpha tensor n alpha is a second rank tensor, which if these guys are locally on average pointing aligned along some axis, this average will be different from the unit tensor divided by the dimension of space. So this combination tells you the degree to which locally these ends are anisotropically distributed. The norm of this tensor, which square the components and add them or whatever you like, and take the square root, that tells you how ordered it is. And the principal axis of this tensor, you can think of as the local axis of alignment. If these are particles with some optical property, this will be the local optical axis. In general, because the second rank tensor in 3 dimensions, notice it's traceless, because if I take n alpha dot n alpha, that's 1. And if you take the trace of the unit tensor, that's exactly the dimension of space. So this is a traceless symmetric tensor. Right? I can maybe even write that down. So it's right. Yeah. Okay. And so these are roughly the 2 ways in which you can describe rod-like or disc-like objects, each of which has a unique normal. And you can talk about their alignment either by saying how aligned their heads are, the head tail-to-head vector itself is, or how aligned the axes are. And you can then build a hydrodynamic theory involving not only the velocity field of the fluid and maybe the density field of the fluid or whatever, but also the orientation field of these objects. And in that equation of motion, you will have to, now we're going to apply our general approach. Okay, what do I mean by that? To fix ideas, let's think that these things actually have a little orientation, a vector field P, okay? I think my description in this section, I happen to have chosen the vector field P rather than the traceless symmetric tensor. I'm using this description. You can do it with either. So then what will I do? I will do whatever I normally do for the hydrodynamics of a fluid, which means, okay, sorry, I have to introduce a bit of notation here. Often it's convenient to work with the momentum density G, right? G is the quantity that you get by, G is the local density of momentum. G is the quantity whose integral over all space is the momentum in that region. Integral over a given region is the momentum, total momentum of particles in that region. So I'll get not only whatever I get for an ordinary fluid, I didn't mention that, I mean, dg over dt will have viscous damping, it'll have pressure, which I should have put in. It'll have couplings of the momentum density or the velocity field to the elasticity of the liquid crystal that it would have even if these were dead Brownian rods, okay? So you may have a bunch of rods, they have some interaction, or maybe they just interact sterically with each other, they can't sit on top of each other. So you'll get some forces governed by some effective Hamiltonians, okay? And you'll have some sort of Hamiltonian dynamics, which I'm writing here only schematically. You'll have viscous damping, you'll have pressure, which I'm afraid I just forgot to put in. You may have thermal or other kinds of noise. But from our point of view, all of those are the dynamics of a liquid crystalline system at thermal equilibrium, which is sort of already known from the 1970s. What we are going to do is to apply our general prescription that these degrees of freedom are coupled to the energy conversion process, what I'm just calling for short, the chemistry. So I'll get some off-diagonal kinetic coefficient. I'm using exactly the notation of the slides last time. I'll get some off-diagonal kinetic coefficient gamma 1, 2, which, because of the algebra of the process I described, has all these other things in it, times the chemical driving force. And what we're going to do is we're going to say this is an active system. That is to say, I'm going to impose the chemical driving force to be some arbitrary constant. I'll call it delta mu. And all the physics goes into the dependence of gamma 1, 2 on the slow variables that we've kept. There will be 2 kinds of terms entering there. One will be terms that are already available in the form of the equations of motion in the absence of activity. And the other will be terms which are still consistent with the spatial symmetries of the system. That is, you will have some, this is an equation of motion for a vector field or a vector density, whatever. you will have here, gamma 1, 2, contributions. You'll have to write down the simplest contribution you can, which is A, a vector, B, built out of P and its gradients, and C, analytic. Okay? So this, and also very important, this equation is a conservation law. It says del G over del T, G is supposed to be a vector field, has to be written as the divergence of some tensor current. Okay, G is a vector. So again, let me maybe write this down.
Sriram, can I ask a question?
Yeah.
Okay. So if I try to draw an analogy between what you wrote down when you developed the formalism yesterday and what you have written down here. So is G equivalent to the capital X or capital
No,
I?
G is one of the slow variables. If you go back here, why is my slide not changing? Just let's see. Yeah. So what I said, if I go back several slides, sorry. Supposing I'm not doing active stuff, I'm just doing, where is my, yeah, hold on a second. So if I just had a simple fluid, mass, momentum, energy are conserved.
Right.
Therefore, rate of change of density of mass, rate of change of density of momentum, rate of change of density of energy are going to be divergences of mass current, momentum current, and energy current.
Right.
The equation I'm now trying to construct is what this equation looks like for an active system.
Okay.
So I'm trying to find the contributions to pi ij, the total stress tensor.
I see.
And there'll be two kinds, ones that are already there in a dead fluid and ones that come from coupling to our X.
Got it.
And then there are two other conditions. One is because it's an active system where energy is being supplied everywhere, we forget about the energy density equation, right? Active hydrodynamics is always a kind of dynamics in which energy conservation is unimportant because you've suffused the system with energy sources, and each active particle is also an energy sink. You write down equations of the mass density and momentum density, and if there are also a bunch of solute particles like the active particles, you write down conservation laws for those guys, right? Yep. So right now, all I want to argue for is the form of the X contribution to this stress tensor pi ij.
Okay, so can I ask a specific question from this slide also? So,
sure.
So there is a commutator of G and
I've just written it schematically. What I'm trying to say is that, okay, that was just, I know, that was just to point out there'll be two kinds of terms in the dynamics. There'll be some terms which are the coarse-grained version of the reversible Hamiltonian dynamics that couples the local momentum density of the fluid to the orientation. So in other words, we're talking about a fluid with an orientable degree of freedom, this P, okay? Yeah. So in addition to the dynamics of an ordinary fluid, even in the absence of activity, you have non-trivial dynamics coming from the back and forth coupling between orientation and flow. If you have a region where the orientation is not uniform, that creates torques which generate flow in the fluid from the elasticity of the liquid crystal. If you have a region where there is a non-uniform flow, that reorients the flow, orientable particles. So, I mean...
so the term with like G, P in this bracket basically captures that contribution.
Yeah, it's captured. I've just very schematically indicated the kind of hydrodynamics. It's basically, supposing you have a liquid crystal display screen. You may have, if you press on that screen, you'll find that the optical contrast changes. Because what's happening is you are squeezing that screen, you're creating flows. Those flows are turning the microscopic orientable particles.
Right.
And so then you're doing two things. You're creating a flow and you're creating distortions in the orientation. Distortion in the orientation creates, I'm saying when you squeeze on it, you're actually producing some local squeezing flow also, but you're also actually messing with the local orientation. So when you create local inhomogeneities in the orientation, that gives rise to flow. Those flows further realign the orientation. that dynamics, the dynamics that you see when you press on a liquid crystal screen on an aeroplane or something, is contained in this term. In this term and in this term. So you're going to write down an equation for the momentum density or the velocity field, and you're going to write down an equation for the orientation field, right? Mm-hmm. Even in the absence of activity, there's a non-trivial dynamics there. It's the viscous and elastic hydrodynamics of the liquid crystal. So I won't describe that in much detail, but all of that is buried in these terms, which is how distortions in the orientation affect the flow. And in these terms, which let me describe these in slightly more detail. Supposing I have an orientation field P, then if the fluid is locally moving, the fluid will carry that orientation, U dot grad P. Okay, that's one part of the story. Secondly, if that fluid has a local vorticity, that will turn the orientation P. That's this term. Okay, this is rotation. This is advection. The third term is if locally you have, again, I think I have got a cartoon for this. If locally you have a shearing flow, a uniaxial flow that you impose, either pushing inward as I've shown here or pulling outward, doesn't matter, that flow will realign the particles. Sorry. So this is how flow couples to flow realigns orientation. This is the system trying to relax the orientation to minimize the free energy functional. This is a more complicated term which we won't worry about. Okay, just ignore this term. This V0 P dot grad P says that if my system is active, then a local vectorial orientation means those guys are traveling. So this will be that P dot grad P term that I mentioned last time. That is, the orientation carries itself because it's active, because these are motile particles. So this page contains two kinds of terms, ones that exist in a dead liquid crystal, which is all the other terms, and one that is there only in a living liquid crystal, namely V0 P dot grad P. That's this page. Okay. Now you can view these terms, omega P, U dot grad P, lambda SP, as terms coming from the microscopic, purely kinematic part of the dynamics, right? At a microscopic level, Hamilton's equations are x dot equals P by M, or x dot is equal to Poisson bracket of x with P times del H by del P, right? Corresponding to that in the momentum equation, right? I'm saying that Hamiltonian dynamics has two parts. One is position changes if there is a momentum. The other is momentum changes if there is a force on the position. You can think of this equation as coming from the trivial, you can think of the omega term, the U dot grad term, and this term as coming from just the way in which movement changes the orientation. And then the other part of that story, the conjugate of that story, is how local inhomogeneities in the orientation affect the flow. And that is this stuff. There's also the things that are already there in a simple fluid, like viscosity, which don't look in detail at the forms of these terms. I'm showing them schematically. Okay. This is a viscous damping term, which I've just shown schematically. This is elastic torques on the liquid crystal. And let me edit this and write down one more term. I'm pretending this is a blackboard. Okay. So the important part of this slide is that apart from all of that stuff, which is already there in a dead liquid crystalline fluid, there is one more term, namely this guy.
Okay, thanks.
Right? And the form of this term you can actually divine from what I told you last time. It's got to be a vector. Okay, one, it's got to be momentum conserving. So it must be the divergence. This is an equation of motion for a vector field G. So this has to be the divergence of some second rank tensor. right? Secondly, I want to build it. The part I'm interested in is the way the orientation contributes to that guy. Third, it's going to be something, okay, crucially, from the general prescription we gave last time, it's got to be some object times delta mu. Delta mu is our parameter that tells us whether the system is active or not. If delta mu is held at some non-zero value, I'm studying the active dynamics of my system. Then it's some, and that coefficient is some off-diagonal kinetic coupling that couples, that makes the force on the x coordinate lead to a change on some other coordinate, right? And now we're going to say gamma 1, 2 has to be the following things. One, it's got to be momentum conserving, so it's got to be the divergence of some second rank tensor, and it's got to be smooth, analytic, all that stuff. And so it'll contain two kinds of terms. One is terms that you could already have from these other parts of the dynamics. We won't worry about those. We'll say at worst what that means is I have to redefine the values of some of the parameters over here. Okay, we'll leave that aside. The crucial thing is what new stuff can come out of here that couldn't come out of this. The simplest such object you can write down, consistent with momentum conservation, i.e. it should be the divergence of some tensor, is something that's the divergence of, sorry for my notation, this is supposed to be the tensor whose components are pi, pj, okay? This is boldface P, tensor, boldface P. My boldface didn't work for some reason. Okay, so the simplest term I can write down is div pp. All right, so the two-part dynamics is one, locally, if I've got an orientation P, I've got a force density div of pp. So if P is completely uniform in space, nothing can happen. Nobody knows which way to go. But if P is locally changing, if P is non-uniform locally, that produces flows proportional to the divergence of pi pj. The second part of the story is those flows reorient P itself. Okay, so it's that coupled dynamics that we're going to look at. Okay, so our equation of motion schematically is the co-moving, co-rotating derivative that I showed you in the previous slide of P is, and then some coupling of the extensional part of the flow to P, downhill descent of P in the free energy functional, and a momentum equation. Now I've done something special to the momentum equation. Remember, I wrote the momentum equation as del G by del T, etc. Okay. I'm going to say we're looking at very slow flows. So that means viscosity dominates. So the flow always quickly adjusts to a value dictated by the forces imposed by the elasticity, pressure, and active processes in the system. So I'm going to ignore inertia. This is like working in the completely overdamped limit. Suppose you had a harmonic oscillator. You had x dot equals P and P dot plus gamma P equals, there is, you know how to write down the equations for a damped harmonic oscillator. In that equation, if you set dP by dt equal to 0, then you have a much simplified equation of motion, a first order equation for the dynamics. I'm working with that and the analog of that picture. Okay. So in my dynamics is whatever the velocity field is, it reorients the orientation. And whatever inhomogeneities you have in the orientation or in the pressure, that drives a fluid flow. I'm going to work in this description in which that fluid flow instantaneously responds everywhere in space to those forces. This is called the Stokesian hydrodynamic approximation. It's a very good approximation for any system on small enough scales and for slow enough flows. And in all the kinds of experimental situations that are usually of concern in soft matter physics, it's perfectly okay to work in that limit. You discard inertia. Any small scale colloidal suspension, small scale flow inside a cell, flow on the scale of a small collection of microorganisms, it's always totally okay to assume the velocity field everywhere knows about the forces everywhere. It just means that viscosity dominates over inertia. We've done a lot of work on the effect of inertia, but I will not talk about it today. Okay. So that's this equation of motion. And what you do, therefore, excuse me, is you take this second equation. Now it's no longer, as I said, it's not a dynamical, sorry, my notation is, remember, several slides ago, I said you can write the momentum density and you can write it as the mass density into the velocity field. So this equation of motion is the equation of motion for the velocity field. U is the velocity field. This is the viscous force density. And the important thing is the balance, the interplay between active forces and viscous forces. If you take this U equation, and you can now say this U equation is an instantaneous relation between U and the stress and the stresses. You solve for U, and therefore the velocity field in this equation, right? Remember, the advection and rotation contains the velocity field, and this alignment part also contains the velocity field. You solve for the velocity field and plug it into this equation. So you solve the Stokes equation for the velocity field in terms of the orientation field, plug it into this equation. And if you take this equation now and ask, okay, I'm in an aligned state. Let's say it's pointing in some direction, which I'm calling P0. And I perturb it with disturbances at wave vector Q about that aligned state. I get a dynamical equation for P, which has two pieces. One is the orientation trying to relax to become uniform so that this free energy functional is satisfied. That takes this form. And one coming from the active processes, which takes this form. Now, this algebra is complicated. I don't expect you to understand this. Understand just the process. Solve the Stokes equation for the velocity field in terms of P, perturb about the mean aligned state with perturbations that vary sinusoidally in space, right? There'll be perturbations with a certain wave vector Q, and write down the effective dynamics. You find two pieces in the relaxation of P, one of which is independent of the wave vector and depends only on the angle, independent of the wave number, depends only on the angle between the wave vector and the ordering direction, and one of which has to do with the relaxation of P to try to produce a locally uniform state. Okay. So this is the effective dynamics. And this sigma A term is the thing that is new. This is the thing that comes from the active processes. I've just renamed this complicated coefficient here. I've renamed it sigma A, sigma active. Okay. So the algebra of this is complicated. I'll show you a cartoon which tries to explain why it happens. Basically, if you have little swimmers of this sort, each of which, this is Prerna swimmers, for example, each of which is trying to pull the fluid towards itself and align and move its body forward, sorry. If you have, let the red line describe the local orientation of a collection of such swimmers, okay? So I've drawn a bunch of red lines here. I'm assuming there's a uniformly aligned state, and now I'm perturbing it by tilting these guys this way, these guys this way, these guys this way, sort of a sinusoidally varying perturbation in the alignment. Now what's going to happen is that over here, if you like, the little polar forces are a little closer together. Over here, they're a little farther apart. Here, they're a little closer together. Here, they're a little farther apart. So the pulling flow will act more strongly, will act more strongly here. And therefore here than here. So it'll create a flow this way. Here, the pulling force will act slightly more strongly here than here, or more localizedly here than here. It'll produce a flow that way. So in this region will get sheared in this way. I assume you can see the heads of the arrows. So this region was already perturbed by tilting to the right. The resulting flow will tilt it more to the right. Okay. If the swimmers had been pushers that are pushing out along their long axis and moving forward, you will get the opposite type of phenomenon. You will get that this is a splay disturbance, this is a bend disturbance. Aligned states of these guys are unstable to bend perturbations that vary like this. Okay. So this is this was a big deal when we came up with it, but I'm using it just to set the stage for what I'm going to tell you about today. This is in bulk fluid. Sorry, I don't need this. This is too much detail. Yeah. So this just tells you that in bulk fluid, if you assume strictly viscous hydrodynamics, aligned states are simply unstable, inescapably unstable. Okay? You take an aligned state, you put in an arbitrarily small perturbation, that perturbation will always grow, as long as you can work in an approximation where you simply neglect inertia. So one interesting direction you can take this in is, okay, what happens if I include inertia? What happens if I keep track of the fact that the velocity field actually has a dynamics and solve this equation and this equation together as fully fledged dynamical equations? What we did just now, as I said, is to pretend that one of the equations isn't a dynamical equation, it's an instantaneous law that defines the velocity in terms of the forces. So I can either say, okay, let's keep track of inertia, or I can say, okay, let's live with this instability of bulk active suspensions in a regime where viscosity dominates, and let's go on and solve other problems. So in my lecture today, I'm going to tell you about, I won't worry about inertia. Okay, what I'm going to tell you about is what happens if I take this system, given in the spirit of the school that we're attending. I'm talking about active matter in complex environments. So the slightly complex environment I'm going to create is, I'm going to say, I'll skip all this. I'm going to say, supposing my active system, I put it in a sort of confining environment, okay? So I've got a bunch of active guys, which I've shown as these red rods here. Rather than looking at a bulk three-dimensional system, I look at a confined two-dimensional system. I place my system between a microscope slide and a cover slip, or a base and a ceiling. Okay, I confine it in the plane. I then ask, what happens to this system? Okay, this is the problem I'm trying to solve. You can look at two kinds of problems here. One where I don't worry about the fact that these swimmers have a head and a tail. I simply only worry about the fact that, look at this cartoon, that each of them is a force dipole. And one where I actually worry about the head-tail aspect, okay? So right now, let me tell you what happens if I look at this, and I describe the alignment using, let me go back a few slides. Using this kind of an order parameter, where the head-tail difference doesn't matter. You think of a bunch of rods described by a tensor of this sort, okay? So now you can say that, you could ask, does anything very dramatic happen, or is it just that now that you've got the walls? Sorry, I should have said one important thing. Sorry, let me just go back. Just give me a second. Yeah. Let's stare at this for 1 minute, okay? This is the dynamics of perturbing an aligned state with a wave vector in some general direction. There are two pieces to the dynamics. One is this guy, which is always making the system relax. It's always stabilizing, but it has a wave number squared. The other is this piece, which has the direction of the wave vector, but doesn't have the magnitude. And what you can see is this, let's assume this factor in here, 1 plus lambda cosine 2 theta, is always stabilizing, okay? And so, for example, let's say lambda is smaller than 1 in magnitude or something. Then the only thing that matters is cosine of 2 theta. Cosine of 2 theta is negative if theta is bigger than, oh God, how do I do this? theta is bigger than pi by 4. So depending on the sign of sigma A, cosine of this term is either positive for angles between 0 and pi by 4 or positive for angles between pi by 4 and pi by 2. So if sigma A is bigger than 0, that corresponds to, where is my cartoon? Yeah, if sigma A is bigger than 0, it corresponds to these kinds of guys. If sigma A is smaller than 0, it corresponds to these kinds of guys. So depending on whether you have this type of swimmer or this type of swimmer, what I told you is, from this cartoon, you know you got an instability either of this sort or of this sort. In this language, it means you get an instability either for wave vector directions between 0 and pi by 4 or wave vector directions between pi by 4 and pi by 2. Regardless, in that unstable regime, the instability takes place only if Q is small enough, right? You've got two terms. You've got a term proportional to sigma A over mu, and you've got a term proportional to K over viscosity times Q squared. So the comparison is between sigma A and K Q squared. Sigma A over K, or K over sigma A, has units of length squared. Okay, so K over sigma A square root is a length. And this term wins over this term if Q is small enough, or equivalently, if wavelengths are larger than this length. Okay, I hope that's clear. I'm trying to be very explicit and very detailed. You have a destabilizing mechanism which is at order wave number to the 0. You have a stabilizing mechanism which is at order wave number squared. Therefore, at small enough wave numbers, while still retaining the Stokesian approximation, at small enough wave numbers, this term always wins. And there's an instability in some region of directions of wave vector, and which region depends on whether the swimmers are pushers or pullers. The important thing, therefore, is there is a length scale. K by sigma has units of length square, and the instability takes place only on length scales big compared to square root K by sigma.
So, Sriram,
K is one of the, yes.
Yeah, so if we compare the terms in the previous equation that you have shown us, so there are terms that are proportional to gamma and lambda, right? So those terms become unimportant at the Q tending to 0 limit?
Right, yeah. Because this term is Q squared.
Okay.
This term is order Q to the 0.
Right. So what about the capital gamma and 1 by mu term that is there for the...
That's just a coefficient, right? K into gamma plus 1 by mu. So what happens is you have... These are all just... Gamma comes from this piece of the dynamics. 1 by mu comes when you solve for the flow terms here from this equation and plug them in. It turns out the effective dynamics has two pieces of order Q squared. One is 1 upon the viscosity times Q squared. The other is the kinetic coefficient here times Q squared. Those two come in together. Gamma, in fact, physically or dimensionally has units of 1 upon viscosity. So these two terms are really the same kind of thing. So basically you have a relaxation. In general, when you have an orientation field in a viscous system, the relaxation rate of that orientation field is an elastic constant into a mobility into wave number squared. And that mobility, roughly speaking, is of order 1 over the viscosity. So it happens that you get two separate contributions, one from the viscous flow itself, and the other from a sort of rotational viscosity or something of the orientation. But they're the same kind of animal, really. Okay. And
gamma
so you have
and
this.
Mu are comparable.
Gamma 1 over gamma and mu, or gamma and 1 by mu are really of the same order of magnitude. And if you go into the microscopic mechanics of what gives rise to them, it's the same kinds of processes.
Got it. Got it.
And so the comparison is between K over mu Q squared and sigma over mu times Q to the 0. So in that comparison, you can see that what really matters is comparing K and sigma, and there's a length squared between them. So you're comparing KQ squared and sigma A. And so I've I just pretended that gamma is also an order one, something of order 1 by mu, and it's sort of cancelled out. In the comparison, the kinetic coefficient cancels out. And I just have sigma A over, I have sigma A over K, or K over sigma A square root. The other important part is that if you look at, yes, yeah.
So when we are talking about underdamped motion and
Yeah.
that we neglect inertia, is it correct
No,
to say that
overdamped motion?
overdamped?
Yeah.
So is it correct to say that we are taking mass 0?
Yeah, actually, it's literally like pretending mass is 0. And you may ask, look, how can that ever be correct? The point is, always on very, very big, really big enough length scales, it turns out you have to worry about inertia. Okay. But it turns out you can do a more detailed analysis of the equations and ask when inertia is unimportant. It will turn out that if all flows at the scale of the individual particles are slow enough that the Reynolds number at the scale of the individual particles is small, then you're always okay neglecting inertia unless you go to some very, very large scales. Okay. So it's not very different from, I'm saying that there's two things. One is that in general, when you go to large wave numbers, damping is more important than the other terms of the equation. Okay. That's one part of the story. But you can really ask when, excuse me. So I'll tell you, I would suggest that I'll give you, if you look, I think that the version of the talk that I sent you guys has hidden the inertia part of the dynamics. I can send you talk slides for the inertial part of the dynamics to ask, when does it matter, when does it not matter? Okay, so that's a whole other talk. It's not the one I'm going to give today. Okay. So, basically you can, excuse me, what you'll find is that if the self-propelling speed is small enough, it will turn out that you can neglect inertia. The real truth of the problem is that there is a much more complete analysis. I am happy to send you guys slides on that part also, and you can understand in full detail what happens. But roughly speaking, on small scales for slow movements, it's okay. All right.
Okay. Thank you, sir.
Sure. So the two important messages from this slide is one, that there is a length scale comparing the Frank constant to the active stress, and two, that there is an important time scale. On length scales big compared to this scale, this term wins. And so the rate of change of the perturbation is that the perturbation grows with a growth rate proportional to the magnitude of the active stress divided by mu. So remember, stress divided by viscosity has units of 1 upon time. Any system which has a scale of stress and a scale of viscosity has a characteristic time scale, mu by sigma A. And what's really happening is that perturbations which are appropriately oriented in space grow at a rate sigma A by mu. So you have, if imagine you had a dynamics dt over delta p is sigma over mu times delta p and nothing else. Then if sigma by mu was positive, then that perturbation will grow exponentially. It will grow exponentially with a time constant mu by sigma A. So you have a wave number, you have a single important time scale for the growth of perturbations on length scales big compared to this characteristic length scale. So it means your aligned system will have kind of uninteresting liquid crystal dynamics on scales small compared to xi, because on scales small compared to xi, this term is important compared to this term. We forget this term, and it has just the overdamped dynamics of a liquid crystal. On scales big compared to xi, it has these growing modes. So if you take your system and you don't resolve it on scales below xi, below this thing, in a coarse-grained sense, what you have is a system in which you have some physics going on small scales, which on big scales is giving rise to the macroscopic alignment always disrupting and destroying itself. Okay? So it's a fluid that is stirring itself. It's a fluid, it's like a bunch of self-stirring units, of each of which is of size psi. Okay, that's what this system looks like if you take a coarse-grained picture. And that was actually confirmed in experiments on active liquid crystals on a substrate. That same phenomenon has been seen on much smaller scales inside a single cell. This phenomenon has actually been placed in evidence by experiments by Shankar and so forth. So this picture, the idea that you have, that, for example, let's take a specific case. Suppose you have extensile or pusher swimmers, then it will go unstable in bend, has been beautifully evidenced by experiments from a group in Barcelona. Also work by Shankar on flows inside a cell. And I don't seem to have the other slide. It's also been seen on a much bigger scale in monolayers of cells. If you take a monolayer tissue, you think it's solid. It's actually a very, very slowly flowing viscous liquid crystal with activity. And this predicted instability has been seen even in those systems. Okay. So there's a lot more physics that goes into it. I will not talk about it. The detailed structure of the instability in 3 dimensions has 2 kinds of failure modes. One is bend with an admixture of splay. The other is bend with an admixture of twist. You can read all about that. What I want to go on to is the following. So now this is really I've actually spent an hour, it looks like, on this part of the story. My God. Okay. All right. My question today is, what happens if I confine it? So we're talking about active matter in confined media. I'm going to confine this system between 2 walls. I'm going to assume that the walls impose a planar alignment, but they don't pick any direction in the XY plane. I'm thinking about a quasi 2-dimensional system. My cartoon that I've drawn here looks like it has only 2 total dimensions. Or you should think of this system as extending out of the board, out of the screen towards you. So, I guess I don't have a picture. So think of the following, that if you can see my hands, let me just stop sharing. Yeah. So, I have one planar surface and another planar surface. So I have, this is my experimental geometry. This is the top surface. This is the bottom surface. And this little sheaf of papers is the active quasi 2-dimensional thin film of active stuff. Okay. Stop sharing. Yeah. So that's my experimental system. Now, and it's confined with a thickness h. So you might think that really all that should happen is that because I've confined in one direction, if that confinement is tight enough, if that confinement is on scales smaller than this active length scale psi, you might think that it should just suppress the instability and everything is very simple. It turns out that, and then you can ask, basically what should happen is, imagine I take my system, I kept confinement on a scale h, which has some value. And now I take my system and I increase the activity by some means. Maybe I change the rate of chemical reaction. Maybe I change the amount of nutrient or whatever it is. As I increase sigma active, psi should decrease. And at some point, psi will become smaller than h. And once psi becomes smaller than h, it's essentially like the unbounded system, and the instability should kick in. You might think that's what happens. Turns out something much more interesting happens, and I'll try to explain to you the fine algebraic details of what happens there. So we'll take a very simple picture, a confined active pneumatic. I won't talk about a vector field P. I won't talk about a tensor field Q. I'll just talk about an orientation field theta. Now I apologize. Earlier I was using theta for the angle between the wave vector and the ordering direction. Unfortunately, now I'm going to use theta to describe the deviation of the orientation from its macroscopic imposed value in this direction. So let's say it's oriented in that direction. Let's call that the y direction or something. And theta is the local perturbation in the orientation away from global alignment. And I'll have, excuse me, a free energy functional, which in a very simplified form is just the square of the gradient of the angle. Don't worry about this concentration field bit. Okay. The complicated, these equations of motion. So let me again go back to these equations of motion for the orientation translated into a description where all that matters is that single angle. Will end up looking like this. You'll have some I'm sorry for further change of notation. I'm sometimes calling it F and sometimes calling it H. This is the term that contains all of the liquid crystalline elasticity. That's what this term gives you. This is the coupling of the angle field to flow. The velocity field, which unfortunately I'm now calling V instead of U, obeys an equation which in this confined geometry, the viscous damping just becomes viscosity. Remember, you have viscous damping in general is viscosity times thickness times gradient squared, right? In this confined geometry, the important gradient, in the lubrication approximation, the important gradient is in this thin direction. So that viscosity times del squared is replaced by viscosity divided by thickness squared. So the dynamics of the velocity field is a balance between viscous forces, which are just a damping coefficient over thickness squared times the velocity, pressure forces, elastic forces, and active forces. And this effective two-dimensional velocity field, the three-dimensional velocity field was 3D incompressible. If you average over the third direction, you now have a 2D incompressible velocity field. You solve this equation for the velocity in terms of the orientation. You plug it back into the velocity contributions to the orientation equation, and you get an effective equation of motion for the angle. All the new physics goes into modeling this active force density. And this is a bit technical, but we'll try to walk you through it as best we can. Okay. The way we do it, let me try to describe the way we do this. One is the force densities coming from the elasticity, which it turns out take a form proportional to one derivative on the local reorienting torque. The torques of reorientation produce these terms in the elasticity. Don't worry about these guys. The important bit is the active guys. What did I say about the active guys? You have to go back many slides, but I'm trying desperately to keep everything connected to what I told you earlier. I said the active stress is P times P. The active force density is a divergence of that P times P. If you translate that into the angle language, those force densities become just some coefficient into our activity parameter delta mu into one space derivative of the angle. Okay. Excuse me. Just a moment. Yeah, I guess that's all right. And this part is a bit hard, I admit. Just. Yeah, okay. Now, here I'm going to do a little bit of a cheat. Okay. The reason I have to do a little bit of a cheat is I have somehow deleted one slide which I wanted. I'm not able to see it here. Yeah. Let's go back a few slides. Yeah, I said my active force density is div of PT. I also said I can think of that P, if I go back a little bit more. I failed to write something down. So just give me a second. Let me actually edit in real time. Hopefully, I've not done any serious. There. All right. So the local average of the microscopic orientation vectors is some vector field P. Its magnitude is how strong the order is. Its direction is something called the director, a unit vector N. All right. Excuse me. So I have an active stress proportional to PP, which means I have an active stress that's proportional to NN, right? So if the magnitude of P is constant, just a moment, sorry. So I'll have an active force density proportional to the div of NN, right? N is the local unit vector that tells you which way P points. So, excuse me for rushing past these guys. If I just took that active force density, sorry, damn it, I need that here. If I just took this guy and imported it, whatever, to my confined two-dimensional geometry, then this active force density would just have a piece proportional to div of NN. That is, I'd get div of NN would be N div N plus N dot grad N with the same coefficient, right? So actually stop me if this is not clear, because I want to explain this part well. So Sumantra, are people perplexed? Are people understanding? I don't know.
There is a question. So
yeah,
just sharing the.
Yes.
So how do you incorporate those as active forces, like those terms?
So that is essentially what I told you back here, right? I just said I write down my equations of motion. And remember my sort of general prescription. I take the equations of motion that I already know that I have in the absence of activity, and I add terms whose form is permitted by the spatial symmetry. Mentally, implicitly, I always think that that coefficient is the chemical driving force delta mu, and there's a factor which is any term that's allowed by the spatial symmetries of this system, right? The simplest term that's allowed by the spatial symmetry of this system and is not already contained in the existing terms is divergence of PP, okay, in this particular case. I mean, I don't know if you're asking about this specific system or in general. The general prescription is you say that there's an off-diagonal coupling to the chemistry. That off-diagonal coupling in general depends on the slow variables. I write down the term with the fewest gradients and fewest powers of the slow variables that I can possibly find that's consistent with the symmetries of the problem. In this case, that simplest term is div of PP, which turns out to be very important, and it gives rise finally when you track it through to this instability that I told you about. So I don't know if I'm answering your question, but when you say, how do you include those terms? The whole first lecture was specifically about the general prescription for how to include those terms. In this particular case, that term turns out to be, the simplest such term turns out to be divergence of PP, which is divergence of NN if you assume the magnitude of P is fixed. So does that answer the question?
Yeah.
Okay. And now I'm going to play a nasty trick on you, which is I'm going to say that's fine, but once I'm in a confined geometry, I can include terms that don't respect momentum conservation. So this is the kind of very strange thing I'm going to do. So let's understand how that might happen. And really, so, as I said this, sadly, I'm not going to cover nearly as much as I'd hoped I'd cover, but maybe it's okay to convey fundamentals and not necessarily to go very far beyond that. So if this was all, then all that would happen is I'd take this same term, and in this confined geometry, I'd say that this FA just gets a term proportional to div NN. So you might imagine, again, you might imagine that it's just, you might think that all that happens is I just take that same term and include it here, okay? But there is an important difference. Look at this term, this dynamics. This dynamics is not momentum conserving. I've got a dynamics of a system between two plates. So the two bounding walls are a momentum sink. My viscous damping is that all the momentum is sucked up by the walls. If I set the fluid in motion at time t equals 0, it gets slowed down and grinds to a halt in a time of order 1 by gamma, right? So the viscous force densities are now not momentum conserving because there are walls. Therefore, I am allowed to consider active forces that are not momentum conserving. So now I will claim that I am liberated from the requirement of having to write down momentum conserving active forces. So rather than div NN,
Hello.
I can break. So here is div of NN. That will contain two pieces. One will be n dot grad n and one will be n times div n, right? I claim, yes.
So I kind of missed the argument that you had for why we don't need to write the momentum conserving terms.
No,
So,
you can write momentum conserving terms, but you are now allowed to not conserve momentum because the effective dynamics of the velocity field,
okay, so
even if it is descent, even if it is descent, looking at long times, so the point is that in this confined layer, if I'm looking at a Z averaged description, right? I mean, this is my picture. This is my picture. I'm going to average over this coordinate and look at the effective two-dimensional dynamics. That effective two-dimensional dynamics has a momentum sink, namely the walls. So I can write down momentum non-conserving dynamics for that velocity field.
Got it.
I'll say that dV over dt plus damping times V equals various forces. And the active forces also can be momentum non-conserving. And so the simplest such active force I can infer is, rather than writing div NN, which will mean that n div n and n dot grad n have to come in with the same coefficient, I can now imagine the simplest and most minimal departure from momentum conservation is I can say that, I've got contributions of the form n div n and contributions of the form n dot grad n, but their coefficients no longer have to agree. For convenience, we'll write them as zeta1 plus zeta2 and zeta1 minus zeta. Just I'm introducing two phenomenological coefficients. One like this, one like this. I could call it A and B, and instead saying that the sum of them is their average is zeta1 and their difference is zeta2, is 2 zeta2. Okay, it's just a notation. If zeta2 was 0, then this term and this term would come in with the same coefficient, and I could rewrite that force density as div nn. But because I'm in this momentum non-conserving geometry, I am liberated from that restriction. And this may seem innocuous, but it turns out to be has a very surprising effect. Meaning, let me again go back. This is, the naive argument would have been that I confine it between two walls, I crank up the activity. Once my active length scale psi becomes smaller than h, it's the essential physics is the physics of the three-dimensional problem. It turns out under confinement, the Z average description, because I'm no longer required to have this momentum conserving force density, allows terms like this. You can argue about what kinds of three-dimensional terms, you have to, okay, look, even if these terms are allowed in this confined geometry, you still have to ask where they came from in the three-dimensional dynamics. And one of those kind of shocking lessons of what we did was that terms that you would normally have neglected in the three-dimensional dynamics because they have too many gradients in them and because they're therefore unimportant, nominally unimportant at large wave vector, turn out to actually matter in this confined geometry. The 2D projection of those terms can turn out to be at low order in gradients in the plane because many of the powers of gradient are replaced by 1 upon h. So this is too technical, I guess, to do without giving you many more slides. But in effect, once I do this, it turns out, I don't know if I have a detailed algebra or not, the effective orientational dynamics of the angle has so, this is algebraically, I won't even try to show you the cartoon. I'll just tell you that the net effect is you get the original elasticity stabilizing term, and you get an active term which now is also at order q squared, okay? But it has a coefficient that involves these two, this new active, new off-diagonal kinetic coefficient, and you can actually get rid of the instability altogether in this confined geometry. Okay, so this is, so I mean, I think, let me not labor it in much more detail. Basically, once you have this independent two independent active force density coefficients, the confined system for a suitable region in parameter space can be stable at all levels of activity. So that's one conclusion. And let me not dwell further on that. It's just that in the plane of flow coupling and ratio of these two active coefficients, there's a region in which no matter how high you take the activity, you're always stable. I do not expect you to understand this in more detail than this, but using the slides that I've already sent you, you will be able to work through it. Okay. Now, supposing, let me spend 5 minutes on what happens in the case. So can I talk till maybe, can I have 10 more minutes total?
Sure.
Okay. Now, this was all in a description where I didn't worry about the fact that these guys are actually moving. I just kept the fact that they're orientable and they're active. Supposing they're motile, supposing I take into account, I could have used a vector order parameter or a purely traceless symmetric tensor order parameter? Let me go to the case for the vector order parameter. What is the effective two-dimensional dynamics of these guys? So there, let me go straight to the confined system. Because I have, okay, and unfortunately, because I assemble these talks from other existing talks, my notation is wildly inconsistent. I've gone back to calling the velocity field U. My apologies, okay? So now, what are my important variables? I've got a vector orientation field P. I've got its free energy functional H. In this confined geometry, its dynamics, if it weren't for fluid flow, would just be dP over dt is minus del H over del P. I've set some kinetic coefficient to 1. The simplest form of the coupling of this P to flow is dP over dt is proportional to U itself. Why is that? This is a system, again, under confinement, as I told you earlier. That means I don't have to worry about Galilean invariance. There is no invariance under U going to U plus constant. I don't have to worry either about momentum conservation or about Galilean invariance. So the simplest coupling I can get for how flow reorients the velocity field is this term. Now, this term has a very natural physical interpretation. If I say dP by dt is constant times U, think of P as the orientation of some object that is anchored to the ground. Imagine you have a building, and on top of that building, you have a little weather vane. These old-fashioned buildings have an arrow or a rooster or something pointing the direction. Especially in the Western world, they have that. This term is just the term that tells you how the direction of the wind reorients that rooster. Right? This is the weathercock term. You understand this picture? So let me unshare for a moment and try to wave my hands a little bit. Supposing this is, suppose this is this arrow or rooster or something mounted on the top of a building. Okay? So here it is. And supposing it's pointing at some angle like this. And supposing the wind comes along this way, it will turn it to point like this. Imagine a top view, okay? Imagine you're viewing it from the top. Let us say it's pointing like this and the wind blows like this, it will turn it like this, right? Sumantra, do you think that was understood?
Yeah, I understood it.
All right,
how many of you
good.
did not understand? Everyone understood.
All right, great. So that's what this term says. If I have a uniform wind flow above and I've got objects anchored to a substrate, remember this term only makes sense if I can talk about an absolute velocity field. I can talk about an absolute velocity field only if I have an absolute frame of reference. That absolute frame of reference is the ground. Or in this experimental geometry, that absolute frame of reference is the confining plates. Okay? With respect to those confining plates, I have an absolute notion of non-zero velocity. Right? So the dynamics, therefore, is dP by dt is U plus relaxational terms. And there's the other part of the story. And in the other part of the story is where active forces come in. I'll write it again. I've neglected inertia. There would be some, mass density times du over dt term. I've set that to 0. This is damping. This is pressure. This is elastic forces coming from the orientation. Everything here except this term would be present in a dead liquid crystal in a fluid film, in a confined fluid film. Now, what is our prescription? We want to write down a term proportional to delta mu, whose name I've changed there. I've just called it V. I want to write down the simplest vector I can in terms of P and its gradients. What's that simplest vector? It's P itself, right? I'm not constrained by Galilean invariance. I don't have to conserve momentum because this is the velocity field of a system confined between two plates. The simplest force density I can write down in terms of P is P itself. What does that mean? Again, let's think of a picture. It's a real pity that I'm not going to be able to do the granular particle stock, but still, it's all right. This term just says, again, let me try to think of what I can. Yeah, look at this experimental geometry. These are both the side view. I don't know if I have a top view anywhere. Yeah, I have a top view here. Yeah. So here is the top view of my confined fluid film. All that this term VP is saying is that here is my system. I want to ask, what do these motile particles do to the fluid film? If I have a local orientation like this pointing here, and let's say it's defined by that vector field P, that's exerting a force on the system, and that force is proportional to P. So all that this term is saying is that if you have a local vectorial orientation P, rather than worrying about div of PP, etc., you just have a local orientation P that exerts a force. So my dynamics of my coupled dynamics of the orientation and flow in a confined active fluid film is actually super simple. It's dP by dt goes as U with some elastic modification, and rho du over dt plus damping gamma U goes as P plus elastic forces, with one important additional feature. This two-dimensional velocity field is that of an incompressible fluid film. So U has to satisfy div U equals 0. And that is done by introducing a grad pi term whose total effect is to ensure that div U is 0. Okay, this pi, we say that pi is a Lagrange multiplier that ensures that div U is 0. So P dot is U plus elastic stuff. U dot plus gamma U is P plus elastic stuff plus pressure. Pressure enforces div U equals 0. What is my prescription next? I'll neglect inertia as I have already done here and solve for U in terms of P. Take that solution, plug it in here, get an effective dynamics of P. What I find is hugely surprising. Basically, the incompressibility creates a funny long-range constraint. Okay, the following thing is important. Supposing I didn't have this U, okay? Then dP by dt would be del H over del P. And I basically get, I don't have a slide for it, sorry. So, basically a uniform P would create no restoring torque. A long wavelength distortion of P would create a restoring torque that goes to 0 as P gets more, as the wavelength gets longer and longer. So I'd get d by dt of the angular deviation of P. I'd get d by dt of the angular deviation of P would be something times some elastic constant into del squared of that angle. What happens here due to the interplay between these two terms, this active term and the incompressibility constraint, is I end up getting a term which is order wave number to the 0. So I haven't shown here. The point is, let me actually put this in. I'm sorry, I'm editing my talk in real time, but you can think of this as me writing on the blackboard. Let's see what it looks like. Excuse me, no, something is wrong. So in other words, if I included the stuff from this free energy functional, that would contribute something at order wave number squared. The active bit, thanks to the weird effects of the incompressibility constraint, turns out to give you a term proportional to the direction, which involves the direction of the wave vector, but for any direction other than purely along the aligning direction, this term is non-zero and it's of order 1. Okay, qy squared over q squared. Supposing qy, it's at 30 degrees or something. It's some number, right? Qy squared over q squared is non-zero for wave number going to 0, as long as qy is non-zero. So the d by dt of the angle field is a term of order 1 and a term of order q squared. And so if the signs of our coefficients are right, the angle field relaxes super rapidly. It relaxes at a rate independent of wave number it seems to be evading Goldstone's theorem. This angle mode is a broken symmetry mode, a number Goldstone mode. Normally, you would expect its relaxation rate to go to 0. Quote unquote, it should be massless. This term acts like, in a field theory language, this term acts like a mass, and this term is like a massless thing, because this term is a true hydrodynamic relaxation going to 0 as Q goes to 0, and this term comes in. So this is really amazing, because what it means is that angle fluctuations are very, very stiff. The hydrodynamic velocity field in this problem acts like the electromagnetic field in gauge theories. It acts like it just as in gauge theories, the sort of electromagnetic field and the number Goldstone would combine together and kill the mass of the number Goldstone problem, and you get screening and so forth. You get a funny screening here. So there's a length, right? This is a Q squared term. This is a order Q to the 0 term. And you end up getting that length scale defined by the interplay of activity and elasticity comes in here as a screening length and gives the number Goldstone mode a non-zero relaxation rate at 0 wave number. If you put in noise, it turns out the angle fluctuations are finite, not divergent, even in 2 dimensions. And you have an anomalously robust long-range ordered state in these systems. Okay.
So
that's a lot. Yes.
So does this explain the experiments with basically this this vibrated granular beds experiment?
So there, I think the point is there, you don't really have an incompressibility constraint. But even in that system, probably if you measure the angle fluctuations, unless you go to very, very large length scales where you can kind of see the compressibility coming in, this physics is sort of present. We have never analyzed the angle fluctuations in that problem in such detail, and probably we should.
Yeah, because it looks very much similar, because there was no transverse fluctuations and it was only going along the longitudinal.
So I don't know, maybe you're right. We have because the experiment didn't have a large enough dynamic range to really look at it. We may have to look at the particle-based simulations to see if this effect is there.
Okay.
So this is a good place to end. You can read the rest of this was for a very different class of systems, particles in a bead medium. I just urge you to read that. I just have no time to cover it. I made a kind of real-time decision to cover something in detail rather than everything sketchily. Okay. So I'll stop here. I'm happy to answer questions.
Yeah, I'm also going to go over the last lectures, like the derivation from the last lecture today as kind of a tutorial.
Right. That'd be great.
Okay. Yep.
So happy to answer if there are more questions.
Yeah, there are.
Okay.
Yeah. So I have a question, like in that confinement geometry where you had 2 walls.
Yeah.
So when you are introducing the active force of this gradient of theta, so that theta, what value does it take at the boundaries?
Okay, hold on a second. Let me just look at my slide. I'm trying to figure out a way of seeing you guys. Spotlight. Okay, so I can see you guys somewhat better. Second. Hide self view. Somehow I'm trying to do hide self view, but it's not agreeing. Okay, doesn't matter. Let me start sharing again. So tell me where you want to go. This slide? No, I mean, repeat your question a little bit.
The slide where you had this active force. Yes, the next one.
Okay, yeah.
So now you have this the derivative of theta along the y and x direction.
Yeah.
So like then I need to have a boundary condition for theta at the walls, right?
When you say walls, you mean the top and bottom walls or the lateral boundaries?
The top and bottom walls.
So right from the beginning, I decided to look at a simple case where at the top and bottom walls, these orientable objects have to lie parallel to the wall and are free to point in any direction in the plane. It's so-called, the liquid crystal people call that degenerate planar alignment. So the walls don't break any of the rotation symmetries in the plane. The system is spontaneously condensed only into an aligned state. But the walls don't, assume the walls have not been further modified to impose any special direction in the plane. Because otherwise this whole dynamics becomes kind of boring.
Okay,
So that is in the top view, these arrows can point anywhere in 2 dimensions. The top and bottom walls don't impose any requirement other than that the guys lie in the plane parallel to the walls.
Okay, yeah. Thank you.
Sure.
Hello.
Yeah.
Thank you, sir, for such a nice talk.
Thank you. Very kind of you.
Yeah. So I have a question that, if we do the 3-dimensional formalism of this problem.
Yeah.
So, like, for the 2D case, we took that momentum.
Yeah, I can hear you.
We need to conserve momentum.
Yeah.
But
yeah.
if we do the 3D formalism, then we can't take this assumption, is it?
Yeah. So in 3D, I have every term has to be momentum conserving. And it turns out that the funny momentum non-conserving 2D terms I wrote down can be derived from fairly complicated but momentum conserving terms in the 3-dimensional case, involving many more gradients. I thought I had included slides on that, but you can read about it in the paper that is cited here. So when I have a bulk 3D system, the momentum can't go anywhere. If I'm treating the system on scales, assume the walls are very, very far away in all directions, and I'm just looking at the dynamics in the interior. That dynamics has to be momentum conserving because it's got no place to go, right? Any momentum change you have in one region has to be because it transfers momentum to neighboring regions. You can't escape that, right? In 2D, because you've got walls, you can say the walls are the momentum sink, and so you can include terms that don't conserve momentum.
Also, it would be a confined region, but we are considering the axis, let's say z-axis.
Okay.
Then only maybe in case of active forces, we are taking this that momentum don't needs to conserve, but there will take momentum conservation into account, right?
Not understanding the question.
I mean, 3-dimensional case also, but it is a confined geometry.
Okay, so then it becomes a question of whether you want. What I was trying to do now is either do a full 3D description or in 2 dimensions, always average over the 3rd direction and get a projected 2D average picture. Okay, so once I do that, I'm allowed to escape momentum conservation. If I want to do something more complicated, namely confined, but I want to describe the physics even on scales basically, if I have something confined like this, let me just go to my slides. Let me go to my screen share again. Yeah, so if I look at this problem, and I want, even with the walls, I want to describe stuff on local scales, then I have to go back to my full 3D equations of motion with boundary conditions. What I'm trying to do is not worry about boundary conditions, say that the net effect of the top and bottom walls is that the Z, rather than taking the 3D velocity field depending on X, Y, and Z, I take a projected or Z average 2D velocity field depending only on X and Y, and say that all the Z dependence has gone into this. I have a picture somewhere. Yeah. If I look at the vertical direction, because there is no slip at the walls for the velocity field, the velocity, any non-zero velocity in the plane will always have a profile in the Z direction that looks like this. And therefore, if I integrate the velocity field over the Z direction and divide by the thickness, that will involve integrating del 2 velocity by del z2 over the third direction. I really wish I could write on a blackboard here. And then that would be del v by del z at the top minus del v by del z at the bottom. Because the velocity is going from a large value to a small value up there, del v by del z is some negative number. At the bottom, del v by del z, v is going from a large value to a small value down here. So del v by del z is positive here. The difference between the negative value of del v by del z here and the value here is some number which is proportional to the center line velocity divided by the thickness. And so you will get a term of this form with a coefficient equal to viscosity divided by thickness squared for the effective. This term gamma v comes from writing viscosity times del squared v, integrating over z and dividing by the thickness. If I don't do that, if I have walls and I want a fully resolved three-dimensional dynamics, then I have no choice but to use the full 3D equations of motion and solve them with boundary conditions. So that's complicated, and I'm avoiding that. That's essentially the answer. Is that what? Did I understand correctly?
Yeah. Yes, sir.
All right, good. Thanks for the question.
Thank you, sir.
Other questions? If not, please thank Professor Sriram Ramaswamy.
Thanks, guys. Bye.
Okay.